walking to self-esteem yesterday.
Oh, it was heartbreaking.
And anyway, this is a paper that's going to appear in Symmetrics 2018. And please give us comments.
Yeah, so this is meant to be interactive, so here's the deal. I'll answer all your questions, but you have to answer all of my questions. The title of the talk is, we're going to talk about moving towards optimality and parallel scheduling. And this is joint work with Moore, my advisor, and Jan-Peter Dorsman, who's in the Netherlands. And like Moore said, this is based on a paper which is going to appear in Sigmetrics 2018. So we want to talk about moving towards optimality and parallel scheduling. And to motivate this a little bit, the thing you need to know is that we really live in a multi-core world. And what I mean by this is that one feature which is common to almost all modern computer systems is that they feature a multi-core architecture. So this could be anything from the smartphone that most of us have in our pockets. Like this iPhone would have 2 cores. I think new models of iPhones have something like 6 cores. This could be the laptop that I'm using to give this talk, which has 4 cores. Or this could be something slightly beefier, like a rack-mounted server. And even a base model rack-mounted server is going to have something like 20 cores. And it wouldn't be at all unusual to see a rack-mounted server with something like 64 cores. But hardware designers have actually presented us kind of an interesting challenge, which is that they've packed all of this processing power into these machines. But they've left it up to the computer architects and the OS designers and programmers to figure out how to translate this processing power into actual performance. And in order to do this, we're going to have to exploit parallelism. And in particular, we can think of this as sort of a resource allocation problem. We've been given this resource, these many cores. We have to figure out how to allocate these resources to the various jobs that we want to run on our system. So I want to start by talking about how this core allocation is done in practice. So to talk about this, it helps to have some picture of a multi-core machine. So here we have some multi-core machine. We'll say it has n cores. So in this case, we'll say that there are n equals 16 cores. And we're going to imagine that a user is going to show up to this system, and they're going to bring with them a job that they want to run. And right off the bat, they're going to be presented with this choice. They're going to be asked, how many cores should I use to run my job? And they're going to have many choices. So clearly, they could just pick any one of these cores, and they could run their job. But they also have this other option, which is that they can try to divide their job up into pieces and run the pieces of these jobs in parallel on the many cores in the system. So they could also choose to run this job on 4 cores. They could choose to run this job on 8 cores. They could choose to split this job up into 16 pieces and run it on all the cores in the system. So given these various choices, what do you think this user is going to choose to do?
16.
16, why not, right? Why wouldn't I try to leverage all of this processing power that I've been given? So this user might try to run their job on all 16 cores. But what I want to emphasize here is that currently in practice, the user is making this decision. They are making this decision about how many cores they want to use to run their jobs. And this is going to become interesting when we consider not just one user running their job in isolation, but a stream of users arriving over time. And each user is going to bring their own job to the system. And they're going to have this same thought. Why not choose 16 cores? What even happens in this case? Well, it turns out that each one of these cores, each one of these orange circles here, is really a time-sharing core. So it's capable of dividing its processing power up and running multiple jobs at a time. And the operating system is going to enforce some sort of fair sharing between all of the jobs that request a specific core. So we can imagine, this blue job is going to come in, it's going to ask to run on all 16 cores, and then all of these other jobs are going to ask for the same thing, and the operating system is going to enforce some sort of fair sharing between all these cores. So this really brings us to the big question I want to ask in this talk, which is, should we be letting the user choose the number of cores they want to run their job on? Is this something that the user is really capable of doing in a good way? And in order to answer this question, I first want to give some background. So to frame the problem a little bit, I want to say that our goal is going to be to minimize mean response time. So what do I mean by this? Well, we're going to consider a job as having some inherent size, which we're going to denote with this random variable x. So you can imagine that every job is going to draw its inherent size, the amount of work required to complete the job from some distribution. And we're not just going to consider one job running in isolation. We're actually going to consider a stream of jobs arriving over time. So you can imagine there's this whole stream of jobs coming in, and they're arriving with some rate like lambda jobs per second. And when a job enters the system, it's going to be work done by some cores, and some time is going to elapse, and then the job is going to be complete, and it's going to exit the system. And we're going to measure this time, the time between when the job arrives and when it's complete. And we're going to call this response time. We'll denote this with the random variable t. And our goal is going to be to minimize the mean response time, the expectation of this random variable t. So we're trying to minimize the average time between when a job arrives at the system and when it's complete. The other thing I want to say in order to answer this sort of big question is that parallelism can be inefficient. So to see what I'm talking about here, I want to talk about something called a speedup function. So on the x-axis here, we have this number of cores k, and I have this thing s of k, some function on the y-axis. And this we call a speedup function is going to denote how many times faster I run on k cores than I would run on a single core. So for example, s of 2 would tell me how many times faster I run on 2 cores than I would run on 1 core. So my question is, what is sort of the best possible speedup function that we could hope to get? Like, let's say I'm running on 2 cores. How many times faster could I hope to run in sort of the best case? I'm feeling like Ellis has an answer.
Twice as fast.
Twice as fast, right? I mean, if I ran more than twice as fast, like, I seem to somehow be violating the laws of physics or something. But maybe I could divide my job up perfectly in such a way that I could run twice as fast. And maybe on 3 cores, I could run 3 times as fast. And I could get something that looks like this green line. This would be like a linear speedup. We would say this job is embarrassingly parallel. We get this perfect speedup. But the question is this realistic? And it turns out that in practice, speedup functions look a lot more like this red line. And what you want to note here is that the speedup we receive is not proportional to the number of cores that we run on. So when I run on 2 cores, I don't quite run twice as fast. And when I run on 3 cores, I don't quite run 3 times as fast. And in particular, we get to this region far out on the speedup curve where things become highly inefficient. When I went from running on 7 cores to running on 8 cores, I really didn't get much of an increase in performance. So in practice, we say that these speedup functions are non-decreasing, they're sublinear in that they lie below this embarrassingly parallel, this linear speedup line, and they're concave. So in light of this information, I want to come back to this question of should we be letting the user pick the number of cores on which they run? And what we find is that there's actually now a trade-off in this system that we didn't initially see. Because initially, we were thinking of things from the user perspective. And from the user's perspective, right, why not run on 16 cores? More cores look better to the user. Even if we were highly inefficient in this area here, more cores look better to the user. But when we look at things from the system perspective, we still see this benefit of running on additional cores, but there's a trade-off. In particular, when we run on more cores, the average rate at which we do work per core has gone down because we use these cores inefficiently. So in some sense, we've added load to the system. And we know from queuing theory that typically when these types of systems experience higher loads, we can expect higher mean response times. So our idea in this talk is that users can't balance this trade-off. They don't have enough information about what's going on in the system. They're too focused on their own job. They're sort of too myopic to see the larger picture. And so instead, we should be letting the system pick the number of cores that each job is going to use to run. Yes?
If you have a lot of users, why can't you just give them 1 core each?
Exactly.
Problem solved.
Problem solved. So it's going to depend on some system parameters, sort of what the right choice is to make. So keep that in mind. That's going to come up later on. But you're exactly right? If we had n jobs in the system, why would we give anyone more than 1 core? We can get sort of perfect parallelism without having to worry at all about the speedup function. So that's exactly the right intuition. So if we're going to let the system make this decision, we have to come up with some possible decisions that our system can make. So what are some choices here? So we have 2 systems here, and each is going to be tasked with running the same set of 4 jobs. And our first choice is maybe we could do something like allocate 4 cores to each job. So we could allocate 4 cores to this blue job, and 4 cores to this purple job, and 4 cores to the green job, and 4 cores to the red job. Or we could do something slightly different. Maybe we want to allocate 8 cores to each job. So we could allocate 8 cores to these blue and purple jobs, and 8 cores to the green job, and 8 cores to the red job. We have to ask which one of these decisions is better. Yeah?
If one of the jobs finishes, do you reallocate that extra space among the remaining jobs?
So when we can do that, that's a very special property that some, but not all workloads have, and we're going to sort of distinguish between these two cases later on. So hold on to that for just one second. And vice versa. So
job arrives, do you ever cut down the number of scores?
So we're either going to assume that jobs have the ability to grow and shrink, or that they have to stay fixed for their entire lifetime. So we'll draw that distinction in just a second. The question we want to ask when comparing these two examples is sort of which is better. And in the system on the left, we can see that each individual job is going to get a smaller speed up, but our system overall is going to be running more efficiently. And in the system on the right, each job is going to get a higher speed up, but we've added a bunch of load to the system. So it's unclear between these two examples which is better. We're basically going to spend the rest of the talk trying to answer this question of when you would make each decision and sort of which is the right choice. So I want to give you an outline of sort of how this is going to go. We're going to start by talking about policies in sort of an idealized world. And we're going to see what's possible there. Can we say something about optimal scheduling policies in sort of an idealized world? Something you might not implement in a real system. And then we're going to ask if we can devise a practical policy that you might actually implement on a real multi-core system. But we'd like to then put this practical policy in context, so we're going to ask if we can compare this practical policy to our idealized world. So let's start with this first question of the idealized world, and here's where this question of growing and shrinking jobs is going to come into play. We're going to consider this idealized world where we're going to give our core allocation policy some sort of like idealized superpowers that might not exist for all workloads in all real systems. And the first of these properties is exactly what you were describing. We say that jobs are malleable if they have this property where they can grow and shrink over time. Right? So a job might come into the system and there might be some optimal number of cores to allocate it based on how the system looks at that moment. But like you said, if a job leaves, now we have all these free cores and we like to be able to reallocate those. So if we can do this sort of reallocation over time where jobs can grow and shrink, we say that jobs are malleable. And this is the case in some real parallel workloads, but certainly not all parallel workloads. The other thing we're going to assume in our sort of idealized world here is that our cores are infinitely divisible. So it's OK for us to allocate sort of a fraction of a core. We can give something like 4.5 cores to a job, and we'll say that it gets some S of 4.5. We assume the speedup curve is some nice smooth line. But again, this is just sort of an idealized assumption. So given these sort of idealized superpowers, I'm going to ask if we can come up with a good scheduling policy. I'm going to ask for some help from you guys. Yeah?
So is the speedup curve the same for all jobs?
Yeah. So we're going to consider the case today where all of the jobs are following a single speedup curve. And we've considered cases where jobs follow multiple speedup curves. It turns out that this problem is hard enough, and that's even more complex question. So yeah, maybe I can answer more about that sort of at the end of the talk if you want to remind me. We'll circle back. So I have this question of what to do with these sort of a core allocation policy. It has these idealized superpowers. So let's say my system's empty and a first job arrives. What do you think I should do?
Give it all the cores.
Why should I give it all the cores?
Because if you need the cores to go work on other things later, you can just take them back.
Exactly. I'm not committing it to anything, right? My job can grow and shrink over time. I might as well run this job as fast as possible, right? So OK, I'm going to allocate all these cores to my single job here. Let's say a second job arrives. What should I do now? What do people think? Yeah.
The best of half cores or each core half?
Right. So let's say I think one of those is probably a good thing to do. Let's say we allocate it maybe like half the cores. And we can extend this idea to say, what if there were 4 jobs in our system?
What do you want to optimize?
What are we?
Expected finishing time.
Yeah, the mean response time, the average time between when a job enters the system and when it's completed.
In this case, shouldn't you think about how much time it takes to finish the job? So if you have a very short job, why do you need to give it eight cores? If you just give it one.
So we're going to assume that we don't know the size of a job.
I don't know. Okay, yeah.
Okay. Right, so there are all sorts of games we could play if we knew exactly job sizes. We could do something like processing the jobs with the shortest remaining processing time or something, but we're going to assume that we don't know the lengths of jobs. Okay. So I'm going to argue if we have these 4 cores in the system, we should basically divide our system up equally. Yeah?
Do you assume every job is like independently from the same distribution?
Yes, we're going to assume that job sizes are IID from some distribution. Yep.
That we know.
We know the distribution. Yep.
So just to make sure I'm following, so there's like implicitly some like trade-off between like load and like speed up that you give each job going on here. We're just erring on the side of like less speed up and less load happens to be better given some parameters of the jobs or something right now.
That's the intuition, and we'll solidify it. But yeah, basically, you're trying to strike this balance between giving jobs a speed up that they can use, but not adding too much load to the system that you've sort of outweighed the benefit of that speed up.
Wouldn't it always be better to just divide them four each if you had 4 jobs?
Yeah, I would argue absolutely. So if we have this situation, I would argue this is a great thing to do. And in particular, this is a policy called EQUI, which says that at each moment in time, we should equally divide the cores in our system between all of the jobs in the system. And notice that we can do this only because of these sort of idealized superpowers, right? The fact that we can sort of grow and shrink jobs over time and that our cores are infinitely divisible allows us to do this. But I think your intuition is correct. So to understand the performance of EQUI, I want to sort of build up our model here and do some analysis. So here's our EQUI system. We need to make some analytic assumptions. In particular, I haven't said anything about the job size distribution, but to make this thing sort of tractable, we're going to assume that this job size distribution is exponential with some rate mu. And what I mean by this is that when a job is run in isolation on a single core, its running time will be distributed exponential with rate mu. Or you can think of that job as finishing with some rate mu jobs per second. We're also going to assume that our jobs are arriving according to some Poisson process. So we said that jobs are arriving with this rate lambda. The fact that it's a Poisson process just means basically at every moment in time, I'm going to flip some coin, and it'll have some probability of coming up heads. And if it comes up heads, I'll say that a job has arrived, and we'll set the probability of that coin coming up heads such that the average number of jobs arriving per second is this rate lambda. That's what I mean by a Poisson process. And once we make these analytic assumptions, it allows us to write down a Markov chain model for the performance of EQUI. And we're going to let the states in our Markov chain be the number of jobs in the system. So here, for example, this state I is denoting the state where there are I jobs in our system when we're running EQUI. But we have to fill in some transition rates. So what do people think about these top transition rates, which are sort of pointing to the right, which are taking us sort of from state I to state I plus 1? Can we say anything about these transition rates based on our model here? Right, it's got to be lambda. This is just our rate of arrivals. Whenever an arrival occurs, the number of jobs in the system is going to go up by 1. What's slightly trickier is to come up with some number for these rates of departure, right? So these transitions are going to occur when a job departs the system. The number of jobs in the system is going to decrease by 1. So let's see if we can fill this in for the case where there's 1 job in the system, right? When there's 1 job in the system, how many cores does that job get? I heard 16 or n. I would say both are kind of correct.
N equals 16.
N equals 16, yeah. So how many times faster is this job going to complete on those n cores than it would complete on a single core? So mu is the rate at which jobs complete. That would be the expected completion time for a single job. So the rate at which the job completes is actually S of n times mu. Okay.
The rate gets faster because your speed,
Yeah.
which means that it would finish. You'd expect it to finish faster.
Yeah, the rate at which we finish the job is getting higher. The expected running time of the job is getting lower, right? So what happens when there are 2 jobs in the system? Now how many cores does each job get? N by 2. So each job is going to complete with some rate S of n by 2 mu. But there are 2 of these jobs, so the total rate of departures is 2 times S of n over 2 mu. And we can extend this to the case where there are 3 jobs. In general, when there are I jobs in the system, we'll complete with rate I times S of n over I. And because we assumed that these cores were sort of infinitely divisible, when we have n or more jobs in the system, it turns out that the rate of completions will just be n times mu. OK, so now that we have this model, I want to see if we can say something about the performance of EQUI. And it turns out that what we can say is that the mean response time under EQUI is actually minimized. So we have this theorem that given exponentially distributed jobs and Poisson arrivals, EQUI is actually optimal in terms of mean response time. And the way to see this is to just look at this Markov chain model and ask what happens in some arbitrary state I. And it turns out that if we can maximize the rate of departures in every state I, we're going to minimize the mean response time. So our claim is that given I jobs, the maximum rate of departures that a policy can achieve is I times S of n over I mu. So let's see why this claim has to hold. We should just look at our speedup function, right? And we always know that given I jobs, one potential allocation is just this equal allocation where every job gets n over I cores. And we can compare this to any unequal allocation. So there might be some other unequal allocation like K1, K2, all the way through Ki. But we know that in order to go from this equal allocation to this unequal allocation, we can think about stealing some cores from some people and giving those cores to other jobs in the system. And we know that the number of cores that we take away has to be equal to the number of cores that we give out, right? The other thing we can see is that there's some cost associated with taking away a core in terms of our total rate of departures, and there's some benefit in terms of giving a core to someone in terms of our rate of departures. And because we know that S is concave, the cost of taking a core away has to be greater than the benefit of giving this core to someone else. So we must be maximizing our overall rate of departures when we're sitting at this equal allocation, at this n over I point.
Could I ask you a question? I'm sorry, this is not about the previous slide. The one with the, you said n mu. Why is the S gone from that function? S is in all the other ones, and then.
So what we're assuming here is that S of 1 is 1. So let's say you had n jobs in the system. Then all of your jobs are running on exactly one core.
Okay.
And S of n is how many times faster do I run on n cores than on one core. So S of 1 we assume is 1.
You have more jobs.
Yeah, exactly.
Okay, sorry.
No, that's fine. That's a totally legitimate question. And we define S of k to be equal to k for k less than 1. So if you're running on less than 1 core, you can think I'm not paying any cost due to parallelization. So it's going to be n mu for all of these higher states. Yeah, good question. So we can see that the total rate of departures is maximized when we're at this equal allocation. So we've proven this claim. So EQUI is maximizing the rate of departures in every state, and therefore is going to be optimal in terms of mean response time. So we had this question of finding an optimal policy in this sort of idealized world where jobs could grow and shrink. And we proposed this policy EQUI, and we show that given some caveats, we can actually show that it's optimal. The question.
Question, is the Poisson process assumption needed to show this it's optimal?
It's certainly needed to write down the Markov chain. That's, in order to assume that things are transitioning with these rates, we need a Poisson process. I don't know if this claim would hold for non-Poisson arrivals. I think in general, very little is known about queuing systems with non-Poisson arrivals. It's hard to say when things are sort of more variable. So I couldn't say for sure. So we've given this sort of idealized policy, but I want to talk about a more practical policy, something you could actually do in a real system. And in particular, I want to come up with a policy that doesn't require this idealized property that allowed jobs to grow and shrink over time. I want to think of a policy that doesn't require us to move a running job. And what I propose is something called a fixed width policy. And this is how a fixed width policy is going to work. A fixed width policy is going to choose some number k, and it's going to run every arriving job on exactly k cores. And furthermore, it's going to choose the k cores which are currently processing the fewest other jobs. So let's see how one of these policies might work. We're in the system where n equals 16, and we're going to consider an example where k equals 4. And the first thing we're going to do to implement this policy is we're going to break our system up into chunks. And we're going to break them up into chunks of size 4. So we say that there are exactly C chunks where C is n over k. So how does this policy work? Well, when a job arrives to the system, the job is going to choose the chunk which is currently processing the fewest other jobs. And notice that this is exactly equivalent to the statement here, choosing the k cores with the fewest other jobs. And it's going to parallelize across all of the cores in that chunk. And we can repeat this for many jobs, right? If a second job arrives, it'll choose one of these empty chunks and it'll parallelize across all the cores in that chunk. We can repeat this for a third job and a fourth job. And even if there's a fifth job that arrives and all of these chunks are busy, we can still do the same thing, although we might have to share our cores with someone else. We're still going to parallelize across all the cores with a given chunk. So hopefully some alarm bells are going off in your head, because there's a really obvious question, which is, how did we choose k? We're like, I just chose k equals 4 arbitrarily here because it made a nice example, but in general, how should we choose k? So I want to talk about how to pick the optimal fixed width for one of these policies, this optimal fixed width k star. And it turns out that by dividing our system into chunks, we actually introduce some really nice symmetry that allows us to apply well-known queuing theoretic results and actually get an expression for the mean response time under these fixed width policies. So we can write down an expression for the mean response time under a fixed width. I'm denoting this ET fixed width as the mean response time under a fixed width policy. And on the x-axis, I have things in terms of system load, which is sort of what these queuing theoretic results require to spit out a response time. So what do I mean by system load? You can think of this system load rho as being the fraction of time that a core is busy when k equals 1. So in other words, if we were just operating the system at maximal efficiency, if we were sending every incoming job to exactly 1 core, this would be the fraction of time that a core in that system is busy. So given this sort of setup, we can just write down the mean response time for one of these fixed width policies. So let's try this when k equals 16. Maybe this kind of looks like what you would expect. When the load is really light, right? When there are not a lot of other jobs in the system, and I'm sending every job to 16 cores, I do very well, because my job gets sped up sort of immensely. But as I add load to the system, as my system load increases, you can think of maybe more jobs arriving over time, the load that gets added by running every job on an inefficient number of cores, this high number of cores, 16, causes mean response time to go through the roof. And the system actually becomes unstable at this point. The mean response time becomes infinite. So similar things are going to happen if we write down the mean response time for lower values of k. So here's when k equals 4, we see we don't do quite as well when the system load is light, but the range of system loads for which we're stable increases significantly. And we can continue this for lower values of k, like k equals 2 and k equals 1. And what this graph is telling us is exactly how to pick k star as a function of system load. So when the system load is very light, we want to just run all of our cores, or all of our jobs on 16 cores. If the system load is slightly higher, we can't really get away with that. We need to run all of our jobs on 4 cores. And again, as load goes up, we'll run on 2 cores. And eventually the load will get so high that all we can do is run our job on 1 core base. So hopefully this addresses some of your intuition before, which is, isn't the best we can do just to run every job on a single core? Yes, but only if there are sufficiently high load that the cores will be saturated. Otherwise, we might as well allocate those cores to someone else. So we had this question of whether we could devise a practical policy. And we said we didn't want to move a running job, and I proposed this policy called fixed width, and I showed you how to pick this optimal level of parallelization k star. But what maybe isn't so obvious is that this is at all a good thing to do, right? We have no way to put these results in sort of context yet. But what I'm going to suggest is that we can actually compare this policy to EQUI, which we were able to analyze in the first part of the talk. So I want to talk about the performance of fixed width versus EQUI. And based on our Markov chain model of EQUI, we can actually pull out an expression for mean response time in terms of the system load. And what we can do is just sort of write these down and see how they compare. So here's our picture of our fixed width policies. And note that we can basically expect to get performance that lies along the envelope of this curve, right, by choosing the optimal k star. So what does EQUI look like? well, EQUI seems to just blow this out of the water. It seems much better. It's stable for, well, it's just as stable as using k equals 1, but over these ranges of load, it's really outperforming our fixed width policy. But this is when the number of cores in the system is 16. And something really interesting is going to happen if we let that number of cores in the system go up to something higher like 512. We get a very different looking picture here. So what we see is that these fixed width policies start to perform much closer to EQUI. And this led us to propose the following theorem, which is that as the number of cores in the system becomes large, the mean response time under our fixed width policy is going to converge to the mean response time under EQUI. So I want to sketch a proof of this theorem for you guys. In general, what we're going to do is we're going to look at these things called critical load points.
Was this a simulation or sort of paraphrasing a simulation chart?
This? No, these are all results of analysis.
Okay.
So we can apply sort of, again, well-known queuing theoretic results to get these colored lines for fixed width. And then we're able to pull out an expression for mean response time of EQUI from that Markov chain model. So these are all analytic results. So what we're going to do is we're going to look at these things called critical load points. And a critical load point refers to the place where we become indifferent between two values of k. So here's a critical load point where we're indifferent between using k equals 16 and k equals 4. Here's another one where we're indifferent between k equals 4 and k equals 2. And here's a point where we're indifferent between k equals 2 and k equals 1. And we're going to look at the performance of our fixed width policy compared to EQUI at these points. And I want you to just recall that we've defined this number c to be the number of chunks in our fixed width system. So this is n over some optimal level of parallelization, k star. And the theorem we have is that at these critical load points, the mean response time under our fixed width policy is actually going to converge to the mean response time under EQUI. So how does this work? Well, we're going to see this by looking at the performance of EQUI at these critical load points. And again, just keep this sort of identity in mind. So we're going to write down our Markov chain model for EQUI. And we're going to look at what happens in this state C. And in particular, I want to call your attention to this rate of departures. So this is c times s of n over c mu, right? This is using the formula for a rate of departures that we derived earlier. But we can actually simplify this, right? Because c is just n over k star. So this rate of departures is actually c times s of k star. OK, let's look at this rate of arrivals. It turns out that we know, if we're looking at one of these critical load points, that this lambda must be c times s of k star mu. That's just the value of lambda that's going to put us at one of these critical load points. The other thing to note is that our expression for the rate of departures, I times s of n over I, that we use to derive all of these rates of departures, is increasing in I. So these two things are equal here, and this expression is increasing in I as we move this way. So we know that these rates of departure are actually less than the arrival rate. So anytime we're in this left side of the chain here, the rate at which jobs are leaving the system is lower than the rate at which jobs are arriving to the system. So we're going to get pushed towards state C when we're here. There's going to be pressure pushing us towards state C. And likewise, when we go to the right side of the chain, because this rate of departures is increasing and this lambda is fixed, now our rate of departures is going to be greater than our rate of arrivals, and there's going to be pressure pushing us back towards C in the other direction. So no matter where we are in this chain, no matter how many jobs there are in the system, we're always being pushed towards this state where there are C jobs in the system. So I want to write down something about the mean number of jobs in the system under EQUI. So we'll have some random variable n, which denotes the mean number of jobs in the system, and I want to talk about its expected value. And it turns out, because there's all of this pressure pushing us towards state C, where we have C jobs in the system, that the mean number of jobs in the system under EQUI is C plus some small factor, some little o of n. And we can apply, again, sort of well-known queuing theoretic results to translate the mean number of jobs in the system to the mean response time. So we apply something called Little's law, which relates the mean number of jobs in the system to the mean response time. And we get this expression for mean response time, which is this C plus little o of n divided by the arrival rate, this C times S of k star mu. And we're going to look at what happens to this expression in the limit as n goes to infinity. Now recall that our c has an n term in here. So as we let n go to infinity, well, this first part of the sum is just going to cancel out to a 1 over s of k star mu. And the second part of the sum here, this little o of n, is going to vanish because we have an n term in our denominator, which is going to infinity. So it turns out that the limit for the mean response time under EQUI as n goes to infinity is 1 over s of k star mu. Maybe that isn't totally clear why this is so great, but it should be a little bit surprising that we were able to get an analysis of the mean response time under EQUI in terms of k star. EQUI has no concept of k star. EQUI knows nothing about fixed width policies, and yet we're able to get some statement about its mean response time in terms of this fixed width, this optimal level of parallelization k star. The other thing that's worth noting is that this 1 over s of k star mu is exactly the expected length of a job when run on k cores in isolation. And if we, again, sort of apply our queuing theoretic results to our analysis of fixed width policies, we can see that this is exactly the limit of mean response time under one of these fixed width policies using the optimal value k star. So in some sense, it's kind of like EQUI begins to behave like a fixed width policy with the optimal k star as the system becomes large. And this was really surprising to us. It's also nice because it tells us that in some sense, these fixed width policies are sufficient to get near optimal performance as the system becomes large. Alice, you have a question?
Yeah, well, so I guess like fixed policy assumes that.
Exactly. Hold on to that for just 1 second. We'll get there in just a minute.
Well,
Yeah.
In the case when s is like linear,
Yeah.
those are all the same.
Yeah. So in
what happened? Like, what would be like the converging point?
So in the case where s is linear, it turns out that there's basically no loss to parallelization. So any policy for which you saturate the cores is going to have sort of the same total rate of departures.
Oh, okay.
Cool. So we had this question about comparing our practical policy to our idealized policy, and we were able to show that the mean response time under fixed width converges to the mean response time under EQUI. So I want to just summarize what we've talked about. We talked about realistic versus sort of best case speedup functions and why these matter, why these create a trade-off when scheduling in these multi-core systems. We then came up with some idealized assumptions for what sort of an ideal world would look like, and we proposed this policy EQUI, which uses the fact that this idealized world has this property that jobs can grow and shrink over time and that cores are infinitely divisible. And given some analytic assumptions, we were able to show that EQUI is optimal. We then said this isn't a practical thing that you'd implement in most systems. So we proposed this fixed width policy, which is much more practical. It just sends every job to some number k cores. And we showed you how to pick k star, the optimal fixed level of parallelization. And we were then surprisingly able to show that the mean response time under one of these fixed width policies is actually pretty good as the size of the system becomes large, as the number of cores in the system becomes large. So now, Ellis, I want to address your concern, which is, does anyone think that these fixed width policies are really as good as we can do? Right? So what are some problems with these fixed width policies? And this is getting into sort of preliminary and future work. So we've done some work on this and we have some results, but I want to give you guys just a flavor of where this is headed. So Ellis's concern was we don't know system load, right? That's a hard thing to know. Does anyone else have concerns about sort of system load in these fixed width policies? Is there anything else? Right? Exactly. We're also assuming that things are constant. And we saw that actually the system could perform really catastrophically badly if the system load becomes too high. We could easily become overloaded, right? What's another problem with fixed width policy besides these issues associated with load? Like, what's a way that we could have another practical policy that sort of seems like it would have to outperform one of these fixed width policies? What was EQUI doing that made it so good, right? It was figuring out sort of when to give lots of cores to jobs and when to give fewer cores to jobs. And with these fixed width policies, we are locking ourselves just sort of very tightly into one number. So what we want to propose,
If we update this, how many jobs we got?
exactly, right? So let's say a job arrives and there are no other jobs in the system. Should we choose K to be high or low?
Choose behind.
Choose to be high, right? Why not? Let's burn those cores. Let's finish the job as quick as possible. But if I arrive and there are like n other jobs in the system and all the cores are busy, probably, yes, that facial expression, right? You probably want to choose K to be low, like 1 or. So what we propose is something called a dynamic width policy. And this is going to address a lot of these concerns, right? So we had these problems with fixed width policies. They're good in the limit, right? But often we don't have arbitrarily large systems. Like this laptop has 4 cores. So you telling me that this policy is good when you had 512 cores doesn't necessarily help me. It also required that we had a fixed and known system load row, right? What we really want is some policy that in some ways is sort of more EQUI-like. It's making more dynamic decisions based on the state of the system. And it still doesn't require these jobs to be malleable. So we're still going to pick some fixed number of cores to run the job on. So our solution is these dynamic width policies that look at the current number of jobs in the system and choose a width for every arriving job based on that number of jobs. And if we look at this graph of our fixed width policies, right, our hope was that through a combination of policies for any given load, we could basically attain the envelope of this curve. But with one of these dynamic policies, dynamic width policies, we could hope to maybe get like some single policy which performs along the envelope of this curve for a range of system loads. So these things are really hard to analyze. And we're really not sure how to do it in our theoretical model. So what we did was we just ran some jobs on real systems. So we took a stream of jobs from the Parsec3 benchmark, which is a benchmark composed of parallel workloads. We ran these streams of jobs on Intel Xeon Phi processors with 64 cores each. And we assigned them fixed numbers of cores based on the number of jobs in the system. We got really promising results. We were basically able to attain the envelope of one of these fixed width cores without knowing anything a priori about the load or the state of the system. So that's really encouraging. And we hope that there's going to be some way going forward. We're going to invent some new techniques to analyze these policies theoretically and say something about how good they perform sort of according to our model. So I want to open it up to questions now. That's pretty much all I have for you guys. Yeah.
So, do you think it's going to be possible to start to replace the jobs have an exact speed up function that you don't know with something more like a traditional parallel model of a job that involves work stealing or something like that?
Ooh, I mean, work stealing is notoriously like terrible to analyze. So that would be a really lofty goal. I would say something that would be more realistic is another one of Moore's students, Zeev Scully, has ongoing research about how to make scheduling decisions given some internal, some information about the internal structure of parallel jobs. So you can think of this as where we assumed things about jobs being exponentially distributed in order to analyze EQUI or some of these other policies. You could think about maybe there are ways to do better if we knew something about the internal structure of these jobs. Maybe we could make more clever scheduling decisions. So I would say that's sort of the way I would go on that. Work stealing seems like it's going to be hard. Yeah.
It seems like your exponential distribution of runtimes is very important for this because it means your memory, the jobs are memoryless, right?
Right.
Otherwise, the fact that you've been running it will tell you something about how much longer it is, and then you might make very different decisions.
So the comment was that memorylessness, these exponentially distributed jobs seem really important to the analysis. The answer is yes and no. So it turns out that all of these systems technically look like what's called a processor sharing system in queuing theory, which means that their performance is actually insensitive to the job size distribution. So all of the analysis I showed you, all of those curves, you would get the exact same numbers given any job size distribution. The thing that changes is all of our claims about optimality. So given if you knew that jobs had some other distribution, like let's say they're deterministic, and so you could tell when you're just about to finish a job, right? Then EQUI is no longer necessarily the optimal thing to do, because you could take advantage of that information in making scheduling decisions. But all the analysis we gave here is still going to hold. So I'd say yes and no. Any other questions?
Well, if not, let's thank our speaker one more time.